Hi there, this is Mr. Deulis here, and we are going to talk about electromagnetic induction today. So, electromagnetic induction is when you induce a voltage by charging the magnetic field around a conductor. So you can see in the image here what's happening is we have somebody who's holding a magnet. So let's say that this is a magnet with a north and south pole to it, and they are moving their hand back and forth, and the magnet is going back and forth within this coil of wire. Coil of wire is generally called a solenoid, but for our purposes, a coil is just fine. So you can see that there's 1, 2, 3, and 4 coils of wire that is then going around to this device that can measure the voltage going back and forth. If it's a continuous voltage, we would call that a voltmeter, but in this case, this is a galvanometer device that's able to measure small amounts of voltages in either direction, and it's just a needle that will point, in one direction versus another direction, depending on the direction of the voltage. So we are moving our hand back and forth, and as you do that, it is going to create some sort of voltage to occur. It is only when the hand is moving. So let's say that the hand is moving in this direction. Then let's say, for example, if I can erase this real quick, then let's say that when you are moving your hand in that direction, that it moves the needle off into sort of this side. Then when you move your hand in the opposite direction, let's say when it's going up, then the needle would go this way. So it actually is going to cause current to flow one way versus the other. It is only when you are moving. If you are static, if you're not moving your hand, then the needle will not move. There needs to be some sort of energy input. There needs to be movement in order to get voltage. Okay, so moving on. If we look at how many loops there are in the system, it is directly correlated to what voltage you get out. The more loops, the more voltage. In fact, it's a direct relationship. So here we have 2 loops, here we have 4, so in this case you would get twice the voltage. Let's see, we have 1, 2, 3, 4, 5, 6. So in this case you would get 3 times the voltage out of this than compared to this one, because it has 3 times more loops. So now we're going to actually ask. So here's our question. I'm going to ask you a series of questions through this lesson. What is the voltage of this second setup? The first setup has 2 loops with 1 volt input, and this one has six loops. What is the voltage output? Okay, so you should have that the answer is 3 volts, because this is 3 times as many loops. So that means we're going to have 3 times as many volts coming out than what we have going, not going in, but rather from this setup. So in this setup, this person is moving the magnet back and forth, and they're, let's say that at any moment in time, they're able to produce 1 volt. If this person over here in this setup were to move this system back and forth, it would, because it has 6 loops, it would produce 3 volts rather than just the 1. Okay, moving on. Faraday's law, it describes the relationship between induced voltage and the rate of change of a magnetic field, meaning that it basically talks about what we were just discussing in terms of the magnet through the loops of wires. It doesn't have to be a loop. You can just move a magnet near a wire, and you can encourage the electrons to move through the wire. The induced voltage in a coil or solenoid is proportional to the product of the number of loops, the cross-sectional area of each loop, and the rate at which the magnetic field changes in those loops, meaning that the area of this loop, so by cross-sectional area of these loops, they're talking about this area of this circle and how many loops there are, and in terms of this last part, the rate at which the magnetic field changes, they're basically talking about how fast you're moving this. So if you're moving this very slowly, then you're going to get a very small voltage output. But if you move it very quickly, then you're going to get, I moved that very badly, if you move it quickly, can't go straight down. There we go. And so you would get a large voltage if you have a quickly changing magnetic field. And that is Faraday's law. Okay, let's move on. A generator. So a generator is a device that converts mechanical energy into electrical energy. So in this case, this person is moving their hand, rotating this thing, so they're going around in this direction, and they're getting this loop of wire to rotate around within the magnetic field. So here you have this U-shaped magnet. Let's just say that this is the north and then this is the south end of the magnet. And so you have a magnetic field that extends from the north to the south end. So there's a magnetic field that is going from top to bottom in our view. And this loop of wire is rotating within that magnetic field. Because of that rotation, because of that energy input, you're going to get electrical output. In this case, it would be an alternating current, unless you have a device called a commutator that would flip the circuit. But we'll talk about that a little bit later. So that's a generator, taking mechanical energy in and getting electrical energy out. A motor, on the other hand, converts electrical energy into mechanical energy. So they're the same device, essentially, just put in reverse. It's a little bit of a white lie. It kind of depends on what kind of generator and motor we're talking about. Actually, a DC motor and a DC generator are the exact same device. A DC generator is otherwise known as an alternator. You might have heard that term before because that's what the DC generator in your car is called. It is an alternator. It converts the mechanical energy of the engine into electrical energy to replenish the battery. So for a motor, which converts electrical energy into mechanical energy, we have some sort of battery or power supply going on here. It could be alternating current, but for simplicity, we're going to talk about direct current. So for a DC motor, which is a little bit more of a simple device than a alternating motor, AC motor, it's again a little bit of a white lie in that regard. But regardless, so we have power input. There's a magnetic field going across, and it is going to force this loop of wire to rotate. Once it gets past 180 degrees of rotation, this mechanism essentially needs to cross paths. The connections need to rotate, and so that's the part of the device called the commutator. And what that's going to do is it's going to allow it to continue to rotate in the same direction. And that's something I'll try and go over in a few minutes. But the bottom line is this. If I go back to this, effectively, if I basically take this same device, and rather than having this person here rotating it, instead, what if I take this light bulb out and instead put a battery in its place? Okay, put the symbol of a battery in here if I can, or at least try to. And so that's the symbol of the battery. Put a battery in its place, and it's going to get this thing to rotate around. It's going to create a motor, sort of. So, moving on. Question 2. What is the difference between a motor and a generator? Well, as we just discussed, motors convert electrical energy into mechanical energy, and generators convert mechanical to electrical. Sometimes they can be virtually the exact same device. In some other cases, they are different. An AC motor is different than a generator. They just operate a bit differently. They have a rotating magnetic field that essentially a magnet on the inside is always trying to catch up to. It's actually a pretty simple device in terms of build, but very different than a generator. All right, so let's move on. And let's talk about the force that acts on a wire that is in a magnetic field. So in this case, we have a magnetic field that is acting from the top of the page going downward, and we have a wire where there's current in that wire going from left to right. So what we're going to do is we're going to apply the right-hand rule into this case, and what I'd like you to actually do while watching this video, I know it might seem weird if somebody's watching you, but I want you to take your right hand, not left hand, that would make it wrong. Your right hand is right. So take your right hand and take your fingertips, take your index finger and point it downward in the direction of the magnetic field. Mind you, There are different ways to apply the right hand rule. This is just my preferred way. So you point your fingers downward with an open hand, and you close your fingers as you make a fist, okay? So you have your open hand with your fingers downward. Close your hand so that way your fingertips, when you start to close your hand, your fingertips are going to be sweeping to the right. And I tell you what, I'll even try my best to draw this, but you're going to have your index finger down, and then your other fingers are going to start to sweep to the right. I know that seems pretty weird. So this is your index finger, and this is your other fingers kind of starting to sweep to the right. And then this is going to be like the most bizarre way to draw it, but this is your thumb pointing towards you. Gosh, that seems just stupid. I can't tell if that even makes any sense to you. But your fingers are down originally. You are closing your fingers into the direction of the current, and then your thumb would have to be pointing towards you. So that means that the force, so your thumb is pointing in the direction of the force. Okay? So the force acting on this wire would be out of the page. The wire itself, if you put current through this wire in a magnetic field that is acting downward, then the wire would literally fling out of the page or of the screen towards you. So let's see if you can get that on a question. Let's see if you can apply that right hand rule. So if we have a magnetic field that is going from left to right, so it's coming from the left of the screen, and it's just continuing to propagate from left to right the entire way across the screen. You have a wire where in the wire there's a current that is going down. By the way, that is conventional current. That is opposite of the direction of the electrons. So conventional current, positive flow going down. In what direction is the force acting on the wire? Take a moment to figure that out. Okay, so if you have a magnetic field, you're going to point your fingers into the direction of the magnetic field, and you are going to try and sweep your fingers downward in the direction of the current. And so if you were doing that, then I don't even know if I can draw this at all. So your fingers go into the direction of the magnetic field, and then you see, I'm trying to think how that would look from your perspective. That's the hand. Here's your other fingers even. Guess you would actually see the knuckle at that point. There we go. It's my best representation. And so your thumb would actually extend out into the page. So this is your thumb, and that'd be the direction of the force. I'm not an artist. I have no idea if that even makes sense from your perspective. But your fingers would start pointing to the right because that's the direction of the magnetic field. As your fingers touch the wire, you can pretend as if the current forces your fingers downwards, closes your hand into a fist, and you point your thumb into the direction that is into the page. So, into the page is our answer here. Okay, so let's talk about what causes a motor to work. That was my phone as I make a video, even though I put my phone on silent. No idea how that happened. Okay, so moving on. So here we have a loop of wire, and we have a magnetic field that's coming from left to right. And so let's put a current through this loop of wire. Let's see, let's choose green for our current. And so we have current that's going to be coming up in this direction. It's going to extend all the way around the loop of wire. So this is the direction of the current as it goes through the different segments of this wire. And let's see what happens. Okay, so let's look at this part of the wire over here, the part where the current is going upwards. So let's apply the right hand rule to this segment of the wire. So your fingers would be going from left to right to start, because that's the direction of the magnetic field. As you sweep your fingers upwards, you would be closing your hand and closing your fist as you sweep in your hand, your fingers upwards. That means that your thumb would have to be pointing towards you. And what we're going to do is we're going to demonstrate or represent this like an arrow. But the arrow is coming towards you. So you would see the tip of the arrow and it would look like that, you know, that tip of the arrow coming towards you. And we're going to represent that in that direction. Okay. In fact, I just really need one of them. So that would be, I'm going to put it right on top of the wire. So that is coming towards us. That means that there's a force. Okay, we often will use that designation for the magnetic field itself, but I'm going to use that for the force. And let's see here. That's the force. Okay, and going across the top, let's see, if we put our fingers to the right and then the current is to the right, it doesn't want to close our hand at all. So there is actually no force at all on this part because it is parallel to the motion of the magnetic field. Only when it's perpendicular to it will there be a force. So let's look at the segment over here. Our fingers go to the right, our fingers sweep down as we close our hand, and we would have a force that is into the page. And to represent that with an arrow, we would see the back side of an arrow, so that would be an X, because we would see the feathers or the back side of the arrow. And so there's a force that is into the page over here. So this whole thing would want to rotate, so that way the right goes into the page and the left comes out of the page. And the whole thing would sort of rotate sort of around in that kind of direction. And it would do that until it gets to a point where this part of this wire is all the way off to the right. When that happens, let me erase some of this stuff. When that happens, then that means that this is over here and so on. What happens is once it gets past that point, then it's going to want to come right back because effectively the current has flipped. So that's why you need a device called a commutator. Once this thing rotates past 90 degrees, the current is going to want to flip and rotate. So every single time this makes half a turn, the commutator needs to switch the current. And so that's how a motor works. Now you're putting current in and you're getting this torque, this rotation out of the system. That is essentially how a motor works. Okay, so I'm not going to actually ask any questions directly on that, but I just kind of wanted to go over it a little bit. Let's look at transformers. They are more than meets the eye. What transformers do at in the most basic levels, they change voltage. So we have two different types. We have a step-up transformer and a step-down. A step-up transformer will increase the voltage. You have more loops coming out than you have going in. For a step-down transformer, it decreases the voltage. You would have more loops coming in than you have going out in that case. Okay, so let's look at this one. 1, 2, 3, 4, 5, 6 coming in. 1, 2, 3, 4, 5, 6, 7. So it looks like we have more loops on the secondary coming out than what we have going in. So that means that this is a step-up transformer. So if we have, let's just say, 100 volts coming in, I know that I'm going to have at least more than 100 volts coming out. But keep in mind that we have the conservation of energy, so you do not get more energy out, you just get more voltage out. Those are not quite the same thing. You would get more voltage out, but remember that power is equal to current times voltage. So if you get more voltage out, that's going to be up. Your current is going to be down. Remember that power is energy per time. So same energy per time, just more voltage, less current. Okay? That's the trade-off. So here's a question. Oh, didn't even mean to make that dot. Which one of these is a step-down transformer? Is it A, B, or C? Which one is a step-down transformer? All right, see if you have an answer here. So our answer is B, the step-down transformer is going to be this one because we have more loops going in than we have coming out. I think there's, 10 loops going in, and we have 4 loops coming out, and so it's going to step down the voltage. You're going to have more current, but less voltage. So here's our equation to kind of figure this out. I mean, I'm sure you can figure it out on your own, but basically we have a primary voltage coming in from the primary side divided by the number of primary turns. So in this case, we have 10. Here we have that's going to equal the secondary voltage. That's the voltage you have coming out of the transformer, divided by the number of secondary turns. So in this case, it looks like we have 4. All right. If we look at this system here, in each case, we have just one loop going around our transformer. By the way, this is a block of iron. That block of iron has its own magnetic field that transfers over to the other side, but I'll have another video to express that further. So the input has the same number of loops for each one of these. In the first case, you have 1 volt coming out with 1 loop. In this case, you have 2 loops, and you're going to have 1 volt for each of them, but if you had, it's 2 volts total. Here we have 2 volts coming out for this galvanometer, and so we have double the loops, double the voltage. So question 5. If 100 volts is coming into the primary side of this transformer, what is the voltage coming out? So let's go ahead and count the number of loops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 coming in for the primary side, and 1, 2, 3, 4, what was it, 5? 5 coming out. So what is the voltage coming out? We have 20 volts coming out. So let's take a look. No, I lied. It's actually 50. So 50 volts is our answer, and let's kind of go through that. So we have the primary voltage that is 100 volts, and I'm going to essentially multiply each side by the number of secondary turns in order to get the secondary voltage alone. So that means I'm going to take 100 times the secondary turns, and that is 5. 1, 2, 3, 4, 5 turns. In fact, I can go ahead and write the units. That's 5 turns. 100 volts times 5 turns divided by the number of primary turns, and that was 10 turns. And notice that turns as a unit actually cancels out. 100 volts times 5 is 500, divided by 10 gives me 50, and our units of volts still stays. So that's going to be 50 volts. All right, moving on. So electrical power is equal to the product of voltage and current, meaning that it's P equals IV. And keep in mind that power in is equal to the power out. So since voltage times current on the primary side, it equals the voltage times current of the secondary side. So that means that the current in times the voltage in equals the current out times the voltage out. So if let's say I have some sort of transformer where I have a certain amount of current coming in, let's just say it's 100 amps, and I have a voltage coming in, let's just say it's a 1,000 volts, and I know what my voltage output is going to be. I always divide each side by the voltage output. And I would be able to solve for how many amps of current I have coming out of that system. And so, lastly, what's the purpose of a transformer? So the purpose of a transformer, and by the way, you always need to have alternating current. I think that's something I probably should have expressed, is that remember, just like how I had expressed, and sorry, I'm going to flip right through these right to the very beginning. Remember, as I expressed, you always have to have the hand moving back and forth in order to get some sort of movement in the galvanometer. So for a transformer, you need to always have current that is changing in order to produce a magnetic field. So it produces a changing magnetic field, and then therefore you always have power coming on the outside. So with that transformer with alternating current, you can have a system where you have, you know, let's say 120,000 volts or even 1,000,000 volts on some high-powered lines, and then in your home you have 120 volts in the United States. Europe uses, in fact, most of the world uses 240 volts, but we use 120. And so why change the voltage? And the reason is for efficiency reasons. I want you to picture this, that the current refers to, effectively, it is how many electrons are moving through the wire at any given point in time. So the higher the current, the more electrons are trying to push their way through the wire. Voltage is essentially how much energy each electron has. So imagine if you have a wire and lots of little electrons that are in that wire. Rather than trying to have lots of electrons push their way through that wire, instead you can give each electron a lot of voltage, a lot of energy, and then you don't need as many of them to actually move through the wire at any given point in time. They don't have to force their way through. And so it's much more efficient to run energy through by having a high voltage, and you're trying to go long distances. High voltage, low current, so the electrons don't have to push their way through as much. Once it gets to your house, then you can go ahead and step it back down because they're not going such a long distance to go from that transformer into your home, and it's a little bit of a safer voltage. Trust me, you don't want to go touching that. Not good fun. But regardless, it does make it significantly safer than 120,000 volts or 1,000,000 volts. So that's the purpose of a transformer. By the way, you might notice a transformer at the end of your street. It would be up on a telephone pole, and it's sort of like a cylindrical sort of thing that maybe is buzzing on a hot day. All right, so I think lastly, that's it. I know it was a long one, but that's kind of my full lesson on the electromagnetic induction. Like I said, I'll post some other stuff to kind of elaborate on a few things, but for the most part, that should about wrap it up, and hope that helps. All right, have a good one.